Thanks everyone for joining. My name's Will. This is going to be a live demo session looking at a specific use case in Wherobots Cloud, specifically analyzing aircraft and weather data. I'm going to show just a few slides, and we're going to jump into getting hands-on, and we'll talk about how you can follow along with the same code example. So let's dive in. So my name's Will. If you don't know me, I work on the developer relations team at Wherobots. Largely my job is making sure that data practitioners are successfully finding insights and working with large-scale spatial data, either with Apache Sedona or some of the things we're building at Wherobots. You can find me online, some of the links there. My email is there also. Feel free to reach out directly if you have any questions. Always happy to chat with folks. So Wherobots is founded by the original creators of Apache Sedona. If you're not familiar with Apache Sedona, it's an open source framework for large scale spatial data processing. It adds spatial functionality, so spatial types, spatial SQL functions, and optimizations for working with large-scale spatial data to distributed compute frameworks like Apache Spark or Flink, Snowflake, Databricks, these sorts of things. And it has great support for interoperability with lots of different spatial data formats. And you can think of the way that we interact with our spatial data in this notebook environment typically, which is what we're going to work through today. So we're going to work through a Python and spatial SQL example in a notebook environment. And at Wherobots, we're building on top of Apache Sedona to build the Spatial Intelligence Cloud. So leveraging the powerful functionality of working with large-scale data in Apache Sedona, but bringing that to a cloud service that manages not just the infrastructure for you, but also builds features and functionality on top of Sedona. So one of those features is bringing this idea of a spatial data lakehouse. So bringing familiar SQL tables as the interface for working with spatial data. We do this by supporting Apache Iceberg, which is a table format, and adding spatial functionality in a version of Apache Iceberg that we call Havasu, which adds things like spatial statistics and spatial functionality for optimizing spatial queries using spatial SQL. So if you're interested in getting started with Wherobots Cloud, anyone can sign up and create a free account, cloud.wherobots.com. And there are some example notebooks that ship with Wherobots Cloud that are available that walk through different features and functionality, different use cases. So that's a great way to get started. So that's kind of all the slides I want to show. Let's take a look at Wherobots Cloud. So here's the main dashboard once you sign in to Wherobots Cloud. And the first thing that you'll want to do is start a notebook runtime environment. The free tier supports the Sedona or Tiny runtime. This is suitable for working with tens of gigabytes level data. And of course, in the professional or pro tier, we have larger clusters that we can spin up. We also recently launched support for GPU runtimes, which brings functionality for running machine learning and AI models as part of our Wherobots AI functionality for things like raster inference for identifying object detection, or segmentation models, things like this that we can run, which we're not going to take a look at today, but we'll talk a bit more about that in a bit here. So let me switch to this other environment. So I've already started a notebook runtime here. This is our New York runtime, which is kind of a medium-sized runtime, and then switched to the notebook environment. So this is an example notebook that we're going to run through. I'll share the code for this after we take a look at this. And so this example is going to be working with aircraft data. We're collecting some data from ADS-B observations. So ADS-B is the way that aircrafts sort of communicate out their location, so that we can, keep track of those, but also they send lots of other information like their heading, their altitude, if there's some sort of emergency squawk, the flight number. All this information is encoded in these ADS-B signals that aircraft are sending out. And then there are various ground sensors where folks are sort of crowdsourcing, collecting, and sharing this data. And there are um, various portals online that sort of collect this data. So we're going to take a look at how we can make use of the ADS-B data to track flights and analyze flight data. And then we're also going to combine that with weather data. So we want to know, can we identify frequently impacted flights based on weather events? We'll do this both with some historical weather data, and then we'll also look at using Doppler radar as a raster product. So we'll take a look at using vector and raster data together. So as we go through this, again, feel free to ask any questions or any comments in the chat. Try to make this as interactive as possible as we go along. So the first thing that we do is create the Sedona context. This is where we can pass in some configuration. So in this case, we're just providing access to a S3 bucket, which is where we're going to be pulling in some of our data. And let me zoom in a little bit so we can make this, yeah, there we go. Hopefully that's a little more readable. So the first thing we're going to do is load our ADS-B flight observation data. This comes from a site called adsb.lol. They collect daily archives of ADS-B data that are crowdsourced from various folks with ground stations monitoring ADS-B and then publish those. So I took, I think, 1 month of observations and converted this to GeoParquet. So we're loading here just over a billion, so this is 1.1 billion observations from this GeoParquet file of ADS-B data. So each observation is a specific point in time and location for a specific aircraft that was observed. So we can look at the schema for this data, and it's actually quite complex. There's a lot of information in here in each one of these pings. We have information about the aircraft, who owns it, what commercial flight it may be connected to, its heading, altitude, a lot of information in there. We can look at the first few rows, and we can see that we have lots of this information in various fields, but one field that's important is we have the geometry field. So that's the location of where this aircraft was observed. And this is a point geometry. So this is point data. So we can query this data using Spatial SQL in Wherobots. Here we're just selecting a few columns. You can see we have this trace struct, so we can select individual fields in the trace struct. And here we're just looking at sort of the first 10 where we have some actual values. So we can see we have things like ground speed, altitude of the flight. This happens to be one single flight, and you can see as it's gaining ground speed and altitude. This, I don't know, maybe is during takeoff or something like that. So let's take a look at some exploratory data analysis. So one thing we can do is maybe try to understand where we're seeing the most aircraft activity. So we want to do some sort of aggregation. And a really nice way to do this sort of spatial aggregation to see how the data is spatially distributed is using H3 hexagons. So H3 hexagons, these are one way that we can tessellate or index spatial data. So what we're doing here is we are for all of our traces. So for all of these aircraft observations, all 1.1 billion of them, we are generating H3 hexagons at level 5. So there's various levels of resolution that we can do. It depends on the size of each hexagon. And within the geometry of each hexagon, we are counting the number of trace observations and then visualizing those using Sedona Kepler. And so we can see here, we zoom in, we can see roughly the size of each of these hexagons and the number of aircraft observations that we have in each one of those. And we can see here, just based on the spatial distribution of the data, we can see lots of flights in North America and Europe. And we kind of lose flight observations over the ocean. And that makes sense because we said that this data, this ADS-B data, is coming from ground sensors. And of course, we don't have any ground sensors over the oceans. So when we go to reconstruct our flight paths from these, we'll have to take that into account. So I see a question in the chat asking about GeoParquet and the differences between GeoParquet and sort of regular Parquet, asking you what sort of metadata do we have? Yeah, that's a great question. So up above here, we said we were loading our data as GeoParquet. So GeoParquet is a specification and standard for working with spatial data in Parquet. If you're not familiar with Parquet, it's a column-oriented data format. That means that we are storing the data from a column next to each other. So it's very good for analytics. So if I want to, grab all of the values in one column and do statistics like, calculate the average or something, it's very efficient to be able to select just one column. There are also lots of optimizations in Parquet for being able to efficiently retrieve data and efficiently store data. So with Parquet, there's lots of really smart compression and encoding that happens to reduce the size of the data stored. But then for efficient retrieval, Parquet is also chunked into like these things called row groups, or typically I would partition a Parquet data set into many different Parquet files. And we have statistics about the values in each column, both in an individual Parquet file and then also in the row group level. And this is good for efficient retrieval because it allows the Parquet reader to prune either certain Parquet files or chunks of Parquet files by inspecting the statistics. So for example, if I was storing information about employees and maybe their salaries, and I want to run a query that says, show me all of the employees that have a salary over $100,000. Our Parquet reader will inspect the statistics for each chunk of data and look at the sort of maximum value in the statistics, and it's able to exclude certain chunks without scanning individual values. And GeoParquet takes this sort of same idea and just specifies how we can store geospatial data in Parquet. And there's a couple of things that the specification entails. One is, how do we encode geospatial data? The initial version of the specification uses WKB, well-known binary encoding. Um, and then the second piece is what metadata is stored. And so we essentially store a minimum bounding box of all the geometries in a Parquet file so that if we have a partitioned Parquet file, the Parquet reader, the GeoParquet reader can inspect those spatial statistics and prune Parquet files to exclude as being outside of the range of a query. If we're searching for all points within a certain polygon, if we can see that in, files 1, 2, and 3, the bounding box is over here, but our area of interest is over here, we can just exclude those. This is called predicate pushdown. So we're able to push down that spatial predicate to the storage layer, which can be very efficient. There's a website, geoparquet.org, that talks a bit more about the GeoParquet specification. The 1.1 specification, I think, is about ready to be cut if it hasn't already. And in the 1.1 specification, there's now spatial statistics at the row group level, which allows us to prune row groups as well as just individual files in a partitioned GeoParquet data set. Cool. So hopefully that answers your question. Essentially, GeoParquet allows us to have more efficient storage and retrieval of geospatial data. I shouldn't say not just geospatial data, but spatial data in general, by really just leveraging a lot of the functionality built into Parquet. And so predicate pushdown is a big piece of that. And we'll see some examples of where that performance comes in a second. Yeah. Thanks for the question. Cool. So we're looking at how we can use these H3 hexagons to sort of aggregate some of our data and have an idea of the spatial distribution of these flight trace observations. And we can start to see, some patterns where it looks like some common routes, some common airport hubs are located. And we were pointing out that we're missing data over the oceans, and we're also, this is not a complete data set. It relies on sort of, crowdsourcing of data. So there are some gaps in the data set. It's not perfect. If we wanted to look at the observations for a specific airline, so maybe we want to understand, what are the flights for a specific airline. We can filter that this way, where in our predicate we're looking for aircraft owned and operated by JetBlue. And we can also filter the trace observations to flight observations that were participating in a commercial flight. So where the flight number starts with JBU. And we can see here, we can visualize that using Sedona Kepler. Cool. So, so I had a question about the H3 aggregation, glimpse of the infrastructure used. Yeah, so we're using we're running this in Wherobots Cloud, which is a service for working with large-scale spatial data using spatial SQL. So we're adding spatial functionality to distributed compute frameworks like Apache Spark. There's a cluster behind the scenes that's managed for us by Wherobots Cloud. And in this case, we're working with the data set of aircraft observations that we've loaded from GeoParquet. And so the spatial SQL functions that we're working with here allow us to do things like tessellate H3 hexagons over the surface of our data. We'll see a lot more examples of these spatial SQL functions. Not sure if that answers your question exactly, but yeah, feel free to clarify it. So let's talk about some of the types of spatial queries that we can run and we'll talk about some of the performance of those. So there are various optimizations built in to Sedona and WherobotsDB for different types of spatial queries. So we'll look at some of those, including spatial range queries, spatial KNN queries, and spatial joins. So let's start off with a spatial range query. So let's imagine that I want to find all of the trace observations within a certain area. So I drew this polygon to roughly approximate the area of the Gulf of Mexico, and I can represent that here. So I can represent the polygon as well-known text, and then in Spatial SQL, I can translate that into an actual geometry type from the well-known text. And then we can create a filter or a predicate here using the st within function. And so this is saying filter for all rows where the geometry, this is going to be the geometry column of our flight observation, where that geometry is within our polygon that we drew here. And so we can apply this filter to our traces data frame. So to the 1.1 billion observations that we have, this takes about 6 seconds to apply that filter. And this is pretty good performance, I think, for spatial range query on a large data set like this. And we can run this a few times to see what sort of performance we get over time. There may be, some differences depending on the state of our cluster and this sort of thing, but 6 seconds is pretty good. And the type of optimizations that are going on here, well, if we think about how our data is partitioned and indexed, we talked about this being a GeoParquet data set with spatial statistics. And so we're able to push down the predicates to the storage layer to be able to prune a lot of rows that we don't need to scan to find points within this polygon. Another type of spatial query that we might want to see is a spatial KNN. So in this case, we're going to find the k nearest geometries. Here we're looking for aircraft observations that are closest to a single point, in this case, the Jackson Hole Airport. So this ST point, this represents the Jackson Hole Airport, and we're calculating the distance to each aircraft observation using ST distance sphere. And then we are finding the observations that are closest. And we end up being able to find the 5 k nearest neighbors in about 17 seconds on our 1.1 billion observation data set. Okay, so before we take a look at spatial join query, so spatial join is where we're combining 2 tables based on spatial proximity, based on some spatial predicate. But before we can do spatial join, we need to have another data set, another table to be able to join against our flight observations. And so we're going to take a look at historical weather event data. And so to do that, we're going to load a data from the Wherobots Open Data Catalog. So one of the benefits of using Wherobots Cloud is that there are several curated data sets that are made available. One of those is a data set of weather events. This is stored in a iceberg Havasu table. So earlier I mentioned the storage layer, this idea of having familiar SQL tables to be able to work with, and the sort of optimizations for spatial functionality are kind of behind the scenes. We don't really have to think about how are we partitioning these tables. We just think about how do we interact them with SQL. Behind the scenes, they're stored as partitioned Parquet files with these familiar iceberg iceberg table format for working with them. So anyway, so we can load the weather table with the Sedona.table function here, and we can see that we have data about the type of weather event, when it occurred, and the location for it. We have 86 million 8 million observations, 8 million severe weather observations. So the first thing we'll do is let's try to have an understanding of areas that are susceptible to frequent severe weather events. And to do this, we're going to use our familiar H3 functions where we are tessellating the surface with at level 5 again, so the same size hexagons that we were using before, and getting a count of the number of historical weather observations that have been of severe level of severity. So this gives us an idea of kind of the distribution of severe weather events historically, which we can now then join with our flight observations. We're now going to do a spatial join, joining our 1.1 billion flight observations with our 8.5 million weather observations. And this is going to, in this case, take just under 20 seconds. And this is going to give us an idea of flight observations that are potentially going to be impacted by historical weather events. What are flight observations that are occurring in areas where we've identified frequent severe weather? And we can look at some of the flights that are most commonly found in areas that have frequent severe weather. And looking at this, it's kind of interesting digging into these. A lot of these are news helicopter flights. So flights that are news helicopters sort of buzzing around certain areas. So far we've been working with point geometries for individual aircraft observations, but when we're talking about flights, these are like line geometries, right? Like a flight route occurs, over time and over a long distance. So let's try to extract some of our flight route information based on these individual point geometries. And again, we'll limit this just to the flights of a single airline. So we're going to filter for JetBlue aircraft that are operating a flight. So where the aircraft is owned by JetBlue and it has a flight number. And then we're going to collect all of the points for an individual flight number by day, so group by flight by day. And then we're going to take all those points and create a line geometry from them. So this will give us for each flight per day, give us the flight route for that flight. Which we can visualize. So you can see here, in some cases, we may have flown multiple legs of that flight in the same day with the same flight number. These are just colored by flight number by day, just to give us a sense. So these are all of the JetBlue flights for 1 month of data. This is, I guess, from January this year. So this gives us a sense of where JetBlue is flying, a few flights to Europe, a lot of flights from the New York area across country to the US, a few to Central America. So now that we have our flight geometry for each route, what we want to do is identify the most impacted flights based on the route, or most potentially impacted by severe weather events. And so while we could do that by joining these route geometries to our flight to our weather data set, what might be more interesting is to have individual flight segments. So we don't want to know just for the entire flight, um, is it frequently passing through areas that experience severe weather events, but can we identify smaller segments that are potentially more disruptive for each flight? And so to do that, what we're going to do is split up each of these line geometries into uniform segments. We're going to say roughly 100-kilometer segments and extract those flight segments. And then for all those flight segments, we'll join those weather with our weather event table. To do this, we're going to use one of the features of Sedona and Wherobots that I think is really powerful, and that is this idea of a user-defined function. So user-defined function, this allows us to write some code in this case in Python, and then we can define that as a UDF, which we can then call from Spatial SQL along with our other analysis. And Sedona and Wherobots integrates with lots of the spatial Python packages like Shapely or Rasterio if we're working with raster data, NumPy, lots of good interoperation there. In this case, we're going to use Shapely. So Shapely is a common geospatial Python library that has lots of great functionality for working with spatial data. And we created a Shapely UDF to take a line geometry and break that up into roughly 100-kilometer segments. So we define this as a Python function. Mainly we're using the Shapely line interpolate function to sort of interpolate points on a line of equal distance apart. And we define that as the interpolate lines function, which we can then call from Spatial SQL. And so now we end up with lots of individual segments rather than just one large line geometry for each flight. So now we're ready to join those flight segments against our weather data. So we'll do a spatial join here using the ST intersect. So where the geometry of the individual flight segment intersects our weather event data, which we can then add in our flight observation as well. So now we're going to group these by flight to see sort of the intensity level for the flight, which we can then visualize. So here we can see our individual segments that, and these are only the segments that intersected with our severe weather event areas that we created previously. And so we can get a sense of what segments are we frequently seeing that are intersecting areas that frequently have severe weather. So this gives us some way to quantify that. So putting this all together, now if we go back and join our entire flight routes now and using this intensity score. So this intensity score, this is fairly simplistic. This is just sort of the number of weather events that each total flight encounters by looking at the individual flight segments. But we can use this as a way to quantify the potential for disruption for the flights. So we can see the flights that have the most uh, potential for disruption, as well as visualizing the areas of severe weather events as well. Cool. So that was a look at using historical weather data to look at potential for flight disruption. Let's take a different look now at using perhaps more real-time data using Doppler radar raster data. So in this case, we're going to look at a sample of NOAA's NextRad Doppler weather data, this is specifically surface reflectivity, which is going to give us some sense of precipitation. So far we've been looking at vector data in Wherobots. So that's essentially geometries and associated attributes. But we can also work with raster data where we're looking at gridded data and cells, and each cell has one or more values associated with that cell. Each cell represents some point on the surface of the Earth, some area in the surface of the Earth. So we're going to load this from a GeoTIFF file, and we're going to do that using this rs from path. So the raster functions in Sedona and Wherobots start with rs instead of st. So we can tell we're working with raster data, and this is going to load a OutDB raster table where we're just loading sort of the metadata for our raster image into the table. We're keeping sort of the actual band values, the actual image on cloud object storage. So this allows us to load very, very large raster data sets and sort of only load the metadata so we can do spatial operations very efficiently. And then only sort of load the actual raster values as we're doing some raster operations. So anyway, we can inspect the metadata. We can see that this is a single band raster image. We can visualize that. So we can see here, this is the continental United States, and we can see there's some pretty significant storms in certain areas. So one thing we might want to do is try to understand for all of the airports out there, are there any airports that are experiencing high precipitation? So in this case, we're going to load airport geometry from a shapefile. So we have a shapefile of airports. And then we're going to join the airport geometry to our raster. So essentially for each point, we're going to, each airport point, we're going to look up, what is the value at that cell in our raster, and then filter where the raster value, in this case, the precipitation index is greater than 100. So this indicates that there is at least a high level of precipitation currently. And we find two airports, Boston and Raleigh-Durham, where we have currently a high level of precipitation. And so now we can do this with this Doppler radar. We can also do this with weather forecast data to have more real-time type of analysis. Cool. So that is the demo I wanted to walk through. That's kind of all I wanted to share. Just to kind of recap what we did, we loaded a ADS-B data set, so aircraft observation. We loaded just about 1.1 billion observations. We did some initial exploratory data analysis. We took a look at some of the types of spatial queries that we can run. We took a look at the performance and sort of how we're able to optimize some of those queries in Sedona and Wherobots. We then added in historical weather event data to identify flights that are susceptible to frequent disruption. And then we created flight routes from that point geometry for a specific airline. We saw how to write shapely user-defined functions to add some additional functionality. In this case, splitting up our flight route geometries into smaller segments and analyze the sort of propensity for disruption based on weather of those individual flight segments, and then to identify the flights with the highest potential for weather impact. Then we saw how to use raster data, in this case, some NOAA Doppler radar data, and then join that with vector data as well to identify some frequently, in this case, to identify airports that were experiencing high precipitation. So this notebook is available on GitHub. I'll share the link. You can find that here in this WBC examples GitHub repository. I'll drop that in the chat here. So you can find the code here. There's some other interesting example notebooks in this GitHub repository as well. There's one that looks at using the new Wherobots AI functionality, this raster inference functionality that I mentioned earlier, as part of a electric vehicle suitability analysis study. You can also find some insurance risk analysis use cases as well. So that's an interesting GitHub repository to take a look at to sort of see how the code works. So feel free to ask any questions that you might have. I see one asking about the size of the cluster that we're running this on. Yeah, that's a good question. So if we take a look here, we were running this in the New York runtime, which is the medium size. So let's zoom in a bit. So we by default, when we sign up for a free Wherobots Cloud account, we have access to the tiny or Sedona runtime. This is 4 executors with 12 cores. We were running this on the medium, which is 24 executors with 144 cores. And we can see, yeah, that represents 576 gigs of memory. We typically, oh, that was for the, right. And we can also select GPU runtimes if we want to run some of the Wherobots AI functionality for raster inference. We want to select the GPU runtime. Those are in preview now for professional tier. So if you're interested in trialing some of that Wherobots AI GPU raster inference functionality, definitely let us know. So you can go to the submit a contact us form on the website or send us an email and we can enable that for you. By default, again, the Sedona runtime is great for testing and development. And then let us know if you're interested in the professional tier, which gives you access to the larger runtimes. Cool. So let me talk about maybe just a couple more slides here, and then we'll continue to take questions. So feel free to drop your questions in the chat. So we said the best way to get started is just signing up for a free account in Wherobots Cloud, cloud.wherobots.com. One thing that you might be interested in is on July 10th, we're going to be running an event with some of the engineers at Wherobots and some of our product folks. So Damien, head of product, will be there as well to talk about the latest features that were released just a few weeks ago in the latest release of Wherobots. So This is the Wherobots AI raster inference functionality that I talked about earlier. We'll also talk about the new Spatial SQL API. So today we saw how to interact with Wherobots in this notebook environment. But the new Spatial SQL API allows us to use database drivers and integrations with other tooling to execute queries in Wherobots. So, for example, we'll see how to use the Python and the Java database driver to work with tools like from within QGIS, but also if we want to orchestrate jobs using Airflow, or if we want to maybe use some sort of like SQL IDE, some sort of SQL editor, we can do that as well. So you can RSVP for this. I'll drop a link to that in the chat. There's the link to register for that event. And then also lots of other resources here. If you're interested in Apache Sedona, information on the Apache Sedona GitHub and Docker image, as well as the Wherobots blog, which is a great resource just to keep track of what we're up to. I'll leave this on the screen for a minute and take a look at the questions here. So a question on the spatial KNN function. Is this part of the Sedona spatial library? Yeah, so let's take a look at that example in the notebook. So spatial KNN was up here when we were looking at the right. So we want to find the 5 observations closest to a specific point. So the k nearest neighbors to this point. And so the question is this part of the Sedona spatial library, or is this part of the spatial SQL standard? Yeah. So we can express this idea of a KNN search in spatial SQL, right? So we're just saying, find the distance to our aircraft flight observations from this point, and then give me the closest 5 using an order by and limit here. So we can express that functionality in spatial SQL. What Sedona and Wherobots adds though is the optimization behind the scenes. So if you think, okay, well, we have a 1.1 billion observation data set, it's going to be very, very inefficient if we sort of scan through all of those and calculate the actual distance and then materialize all that to then do an order by and the limit. And so what Sedona adds is the optimization in the query plan to efficiently execute this query using the partitioning and indexes throughout the cluster to efficiently execute this query. In this case, this takes 17 seconds on a billion row data set. Yeah, it's a great question there. Another question about recommendations for displaying spatial route visualization using dashboard tools. Yeah, so within Sedona and Wherobots, we were using this Kepler integration. So Kepler GL is a GPU accelerated visualization library. In this case, we're using the Sedona integration within the Jupyter Notebook. So this is a good option. LeafMap is another Python library for visualizing spatial data that supports different rendering options. So we can use like MapLibre to render. There's a Kepler renderer for it, as well as a Lawnboard renderer, which is an interesting project for leveraging GeoArrow to visualize large scale spatial data. So I think it kind of depends on, um, I guess, when you're asking about in a dashboard environment. So maybe you want like some sort of like web rendering library. Yeah, I would have a look um, at some of the web visualization tools, MapLibre. Take a look at Longboard and Kepler as well. Yeah, kind of depends on what your stack looks like. And then is Django compatible for implementing these visualizations? So Django is a Python library for integrating with databases. There's a Geo Django package that might be interesting to look at. I'm not aware of any specific Sedona Wherobots Django integration, but with uh, the Python driver, you could possibly um, connect those two pieces together. That might be an approach to take. Cool. Let me look through the chat here and make sure we answer any other questions. Otherwise, we're about out of time here, so feel free to ask any last minute questions. Couple, yep, couple in the chat. Cool. Think we covered everything here that I see in the chat. So, yeah, feel free to reach out if you have any questions. I'll put my contact info on the screen here. So, thanks everyone for joining today. I dropped a link to the code in the chat, and we'll be sure to send out a follow-up email that has a link to all these resources and the slides and the code as well. But yeah, thanks everyone for joining today. Feel free to sign up for a free Wherobots Cloud account, and I think that's kind of the best way to get started. Is just kind of dig in and try to see how to maybe load some of the data relevant for the types of use cases that you have. Yeah. Well, thanks everyone for joining today, and uh, again, if you're interested in seeing some of the latest functionality that we released in the most recent release of Wherobots Cloud, you can sign up for the Wherobots Release Overview webinar, which is happening July 10th. So hope to see you there. And again, great to see everyone today. Thanks a lot for joining, and we'll see you next time. Cheers.